Hello folks, this next video covers angles and radian measures. So the first part of 6.1. So if you recall our unit circle, um, we measured all of our angles in the unit circle in degrees. So the other types of units of measure that we can measure angles in are called radians. So it's kind of like, how we can measure length in inches or centimeters or kilometers or miles. Like, it wouldn't make sense to measure your house in square miles, right? That's why when we buy houses, we see them listed in square feet, and it wouldn't be normal to measure the distance from me in Dallas to you down in Portland in feet. It makes more sense to measure that in miles. So sometimes for angles, it's actually better to use what are called radians. So it's kind of like just a different type of measure other than a degree. So if I give you this circle here, and let's say we have a point on the circle. So if I have an XY axis and I have a point on a circle, we'll call that point P and we'll call that XY. And this point on the circle, it's on the unit circle, so I know that this should be 1. Then by the use of the distance formula, now obviously I know the distance already, right? So I'm not really trying to find the distance, but I'm just trying to use the distance formula to establish kind of a definition. So by the distance formula, this point P, if this is the origin, would be a length of, like x2 minus x1 squared plus y2 minus y1 squared, or y2 minus y1 squared. Using that formula, we would have x minus 0 squared plus y minus 0 squared is equal to r squared, which is 1. And then if we square both sides and simplify, x minus 0 is still just x, so then we get x squared plus y squared is equal to 1. So if you recall, this is the equation of a circle. From, you may have seen that back in Algebra 2 or in geometry, an equation of a circle. Now this is the equation specifically of the unit circle that does not move its center from the origin, that has a radius of 1. Now, I want you to consider on this unit circle angle alpha. So if I want to look at this red angle here, and I'm going to call it angle alpha, radian measure, let's write this down because this is important to kind of understand the difference between the two. Radian measure is defined as the length of the corresponding arc of the unit circle, which we're going to refer to as S. Okay, so that means the measure of alpha is going to be S radians. So it's going to be this length of this arc here that we refer to as S. Okay, so alpha is going to be S radians. Now, recall back from your geometry days that essentially this is just a piece of the circumference. So if we recall that the circumference of a circle can be found by computing either pi d, but we're going to do 2 pi r since we know that the radius is 1, right? So then this implies 2 times pi times 1 is just 2 pi. So what that means is we've been referring to our unit circle with degree measure. So that means 360 degrees, a complete revolution, can be now also referred to as 2 pi. Is one complete revolution. Similarly, we can say, okay, well, half the circle or semicircle will be 2 pi divided by 2, which is going to be pi. And then we can divide 180 in half and get 90, and we can divide pi in half and literally get pi over 2, or 1/2 pi. And then 45 degrees can be again, all we're doing is cutting in half each time. So a half cut into a half will be pi over 4. And this is, there are obviously all of the measures. In fact, if we actually look at this unit circle here, your pi plates that we've done before can actually be just filled out even more to include the angle measures as well as, let me try using this, the angle measures as well as, oh lovely, stretching. Oh, haven't y'all missed me being all weird and things? Yeah, I'm not gonna fix that. There we go. So anyway, what this now allows you to do is just refer to location on the unit circle with other numbers instead of just the degrees. So obviously these degrees here in the middle are what we're familiar with, but now we can refer to all of the radian measures as well. So you see 360 degrees, well, technically 0. So let's look at 180 is the same as pi. We just talked about that one up here. 90 is pi over 2. So these two are the same, and 270 is 3 pi over 2. So you see all of the angles can be referred to, or can be matched with a radian measure and not just degrees. So going a little bit further, we can say that 1 radian, if I actually want to talk about measure, like, okay, well, what does a radian actually equal and something that we can understand? If a radian is going to be 180 over pi degrees, if we actually calculated that, that would be approximately 57.3 degrees. So if you wanted to compare it to something that you understand a little bit better, and conversely, we can say, okay, well, 1 degree is about pi over 180 radians, which is approximately 0.017 radians, so a lot smaller. Now, radians, we don't use R or anything like that for radians. We just understand typically with radians, we use pi. So anytime, if you see an angle measure is 3 pi over 4, then we know that that is radians. Degrees will always use the degree symbol, but there is no symbol for radians. So you can see with what we just did here that if 180 over pi using this chart, so over here we established that 180 degrees is equal to pi radians. So when I write 180 degrees over pi, this is essentially, well, I can do the reciprocal as well, so that's the same thing as pi radians over 180 degrees. These two are equivalent to one another because they are both equal to the number 1 because it's the same number over itself, just a different representation. So it's the same thing as me trying to write, like 12 inches is equal to 1 foot. Those things are equivalent to each other. So it doesn't mean 12 over 1 equals 1. It means 12 inches over 1 foot can be reestablished as 1. Okay, so we can do things like conversion. So if you didn't have your unit circle completely memorized, which you shouldn't, that's a lot of added numbers now doing all these fractions, you can convert. So I can ask you to change 330 degrees to radians. And all we have to do is just change the way that it looks. So if I have 330 degrees, and I want to change it to radians, then we simply need to multiply by that one of these versions of the number 1 to change the way that it looks. We're going to multiply by pi over 180. If I'm trying to get to radians, I want pi to be in my answer. So that's why I'm choosing pi over 180, because you'll see when we multiply straight across, right, numerator with numerator, denominator with denominator, then we get 330 pi over 180. And then in your calculator, you can go ahead and just reduce 330 over 180, hit math, enter, enter, get that as simplified as you can. You get 11 pi over 6. You say, well, Ms. Schwanner, why do you pick pi over 180, not 180 over pi? Well, imagine if I multiplied by 180 over pi, I am kind of complicating the problem slightly by getting a super, super large degree, and we never have radians with pi in the denominator. That doesn't really make sense. Okay. Conversely, we can also change radians to degrees. So I can say, okay, change, let's do 2 pi over 3. Again, no symbol, but because the pi is there, we understand it's radians. 2 degrees. Okay, so in this case, we have 2 pi over 3. And I'm trying to go to degrees, which for degrees we don't use pi. So if I want to eliminate pi, and I'm trying to choose between which one of these versions of 1 I'm going to multiply by, to eliminate pi, I want pi in the denominator. So I'm going to multiply that by 180 over pi. That way, when I multiply straight across, then I end up with, let's see, 2 times 180 is 360 pi over 3 pi, and then the whole reason for doing that is because pi over pi cancels. And then 360 divided by 3 is equal to 120 degrees. So that's simply how you do the conversion. Just multiply either by 180 over pi or pi over 180. Okay? Now, let's recall something from before Christmas break. So, actually putting some of these into practice. If I asked you before Christmas break to evaluate the sine of 210 degrees, essentially what I'm asking, now if you had your unit circle, that's really easy, right? We remember that sine is the y coordinate. Right now, sine, yes, is technically opposite over hypotenuse, but in the unit circle, we know that sine is y over r, but if we know that the radius in the unit circle is 1, then the sine is always just y. So if you have the unit circle, then all you do is simply locate, what did I say, 210. So you locate your 210 degree angle, which is here. You look at your sine value and ta-da, you're done. But unless you're going to generate the whole unit circle, typically we just generate the first quadrant. So the first thing we did, let's say, okay, first we want to find a reference angle, which is going to be the angle of reference in the first quadrant. To find that, we're going to do 210 degrees minus 180 degrees, and you get 30 degrees. Okay, so what that meant was if you were able to generate the first quadrant of your unit circle, then you should know that 30 degrees has a coordinate of the square root of 3 over 2, comma 1/2. So since this is the reference angle for 210, that implies that 210 degrees, the only difference is that this one is in quadrant 3. So the only difference is that 210 is going to be negative square root of 3 over 2, negative 1/2, which implies that the sine, we know, is the y value of 210 degrees is just the y. So it's going to be negative 1/2. So we're able to do that with our knowledge from before Christmas break. The only difference between then and now is that I may not always give you your angle in a degree. You may be given the angle in a radian. So, for instance, I may ask you to evaluate the cosine of 4 pi over 3. Again, if you can see the whole unit circle, and you remember that cosine is the x coordinate, then you just look at your unit circle, look for your x coordinate at this angle, and you're done. That may not be easy for everyone. So you have two options. Option number one is to first convert, let me write these. Option one is to first convert 4 pi over 3 to degrees and solve like previous example, doing those steps that we just did in that problem. Okay, option two is usually more likely because honestly radians are a lot more common and used in trig and in pre-cal than the degrees are. So option two is actually sticking with the radian measure and proceeding. So, you know, we do the same steps but still just dealing with radians. So again, we first want to find a reference angle. Well, the only difference is instead of subtracting, we're still in the third quadrant, right? 4 pi over 3. If you know that let's see, if you know that 180 degrees is pi, then 4 pi over 3 you should know is in the third quadrant. So you kind of have to be pretty comfortable with your fractions here. In the third quadrant, in order to find the reference angle, we subtract 180, just like we did in this example. So instead of 180, since we're dealing with radians, we're going to subtract pi. So I'm going to take 4 pi over 3 minus pi. Now, 4 pi over 3 minus pi is not 4/3. The pi's don't just subtract. If I'm subtracting fractions, I have to have common denominators. So I'm going to do 4 pi over 3. I need this guy to also have a denominator of 3. So I can say, well, that's the same thing as 3 pi over 3. And now that I have common denominators, I can just subtract 4 pi minus 3 pi, which is pi, over 3. So my reference angle is pi over 3. So remember, we did this because this is like 180 degrees. Okay, now since pi over 3, so there's our reference angle, that's equal to 60 degrees. If that triggers your first quadrant knowledge, then hopefully you know the coordinates. So then the reference angle coordinates at 60 degrees is 1/2 square root of 3 over 2, which implies that at 4 pi over 3, the only difference between our reference angle and ours, which is in the third quadrant, is that again they are both negative. So negative 1/2, negative square root of 3 over 2, which implies, again, we're dealing with cosine, which is the x value, so that implies that the cosine of 4 pi over 3 is negative 1/2. Okay, so that's how to actually evaluate radians of specific coordinates. Okay, we can go a little bit further and actually compute I'm trying to look for a word. You can also do things like area and circumference of a circle, but just certain parts of it. So let's see if this triggers something. You did this back in geometry, but you did it with degrees. So you found it was called areas of sectors and arc length back in geometry. It's still called the same thing here, but we're going to find it using radians instead. Okay, so we're first going to talk about arc length. So arc length is, instead of me asking you for like the entire circumference, let's look at like of this red circle per se. If I don't want to look for the entire circumference and I just want to find like a portion of it, that's where this is going to come in handy. Excuse me. Okay. Now, the length of a circular arc is defined by the central angle that intercepts it. Okay, so like a central angle means its vertex is at the center of the circle, or in this case, the x and the y axis. Okay, so this a piece of a circumference. So suppose I have these two concentric circles, and I'm going to say that r is the radius of the big circle. So let's do this. If this is about the center, and we'll call this. So r is the radius of the big circle, and we'll say the smaller circle is the unit circle. So we're going to say that its radius is 1. And then let's say that the central angle is theta radians. So we need to actually create an angle here. So the central angle is, remember, like I said a second ago, its vertex is the center of the circle. So it's going to be theta radians. And it intercepts arc TU on the unit circle. So arc TU is this arc here. So what intercepted means it just opens up to that arc. So it intercepts TU on the unit circle, and it intercepts arc KW on the bigger circle. If we suppose that KW, so the arc, let me get a different color, the length of this arc is S. So if we call that distance S, And we don't have a distance formula for that. Well, I mean, we kind of, that's what we're trying to find. It's a curve, so we can't calculate the distance straight. So we got to use what we know about circles. So if I call that distance, that circular length from arc KW, the length S, and then let's say we know TU, the arc TU is theta, and that's just by definition of the unit circle and its central angle. These two measures are going to be the same because it's the central angle of the unit circle. Then we can use this proportion. This allows us to set up, since these circles are concentric, meaning they share the same center point, that allows us to say that S, the length of the big arc here, to theta, that proportion should be the same as the ratio of the radii. So the big radius we said is r, and the small radius of the unit circle we said is 1. Well, if I'm trying to solve for s, right, I can just cross multiply. And if I cross multiply, then I get s is equal to r times theta. Well, this is the formula for arc length. A lot simpler than the one you learned in geometry, because the one in geometry had to deal with degrees. This one deals with radians. Now, I don't want you to get confused with this R standing for radians. This R stands for radius of the circle, so the length of the radius, and then theta is the length, the angle measure in radians. So angle measure in radians. Okay, so we can use this to answer questions like this. Find S, but given a circle, let me actually use a good circle. Okay, so if I define this circle, let's see, center point's here, and let's say we have just this angle, and this is 128 degrees, and I want to find S, this length of this arc here, given that the radius of the circle is 5 centimeters. Well, it's actually rather quite simple. The only thing that you have to remember to do is that this equation that we wrote requires the angle measure to be in radians. So the first thing you want to do is convert 128 degrees into radians. So to do that, we're going to multiply 128, multiply that by pi over 180. And then we multiply straight across. Remember, this is technically over 1, so then we get 128 pi over 180. In your calculator, don't worry about pi, just type in the numbers out front to simplify that fraction. Hit math, enter, and you should get 32 pi over 45. So now this is theta. So then if the length S is r times theta, we know the radius is 5, and we know theta is now 32 pi over 45. The math is super simple, y'all. I think the area where some of us may struggle is literally typing this into the calculator. So this is 5, not S. You've got to make sure you make use of parentheses around these fractions in order to do this well. Also, side note, for pi, you actually need to type that in your calculator, and that's going to be on the second. So you have to use the second, and then it's on the caret button, and it actually enters the number pi for you. So make sure to use actual pi, never 3.14. Use parentheses around your fractions. For the sake of this video, we'll round to the nearest tenth, so we'll say that that arc length should be approximately 11.2 centimeters. Okay, so that's dealing with length. We can also find area. Now, the area of a full circle we know is pi r squared, right? But we can also find the area of just a portion of the circle. When that happens, that's called a sector. So we can say a sector of a circle. A sector of a, let's spell circle correctly. A sector of a circle Uh-oh, uh-oh. Phew, okay. Sector of a circle is a region. Bounded by a central angle. Is a region bounded by a central angle and the intercepted arc. My favorite visual for this is a slice of pizza. So area of the circle would be this whole thing. A sector is literally a section, or just a portion. So that is a sector. Now, you could easily find that if you knew the degree measure, which is what you did back in geometry. And it's actually even more, or it's actually even simpler if we know the radian measure. Okay, so using what we know about the unit circle in any circle, we can say that the ratio of the area of a sector, so we could say the area of a sector, to that of the whole circle, so the area of the sector compared to the area of the circle, this ratio should equal the ratio of its arc length, which we referred to as S in the definition above, over the full length, which we refer to as the circumference. So using what we know, we can actually add a little bit more to this and say that we'll just call area of a sector A by now. We all know that the area of a circle is pi r squared. We know that arc length we defined earlier is that S is equal to r times theta. So this is going to be r times theta over, we know the circumference of a circle is 2 pi r. So if I solve for A, if I multiply, so if I try to get rid of pi r squared on both sides so that it cancels, and I multiply both sides by pi r squared, then I get A is equal to r times theta times pi r squared over 2 pi r, right? Because this technically has a denominator of 1, multiply straight across. And then we cancel out our like terms over each other. Pi over pi cancels, r over r cancels, leaving us, you'll see it, I'll say textbook-wise, or like if you were looking at a reference sheet, you would actually see this written as the area is equal to 1/2 theta r squared. Actually, you would see theta last. Usually, you would see 1/2 r squared theta. So this is the formula for the area of a sector of a circle. So all you need to know is the radius again and the angle. And then the examples are actually quite simple. I can just say find the area of a sector given this following information. So get you a circle, and let's say that the central angle is 5 pi over 6 radians, and let's say that the radius is 16 centimeters. Well, now I made this one easy. I didn't even give you degrees, I just gave you the radians that you need. So again, if we say area is 1/2 radius squared times the angle theta, then we got 1/2 times 16 squared times 5 pi over 6. And again, just be super cautious plugging this in your calculator. I would actually compute 16 squared first, which is 256, and then 1/2 of 256 is 128, and then 5 pi over 6. Again, make sure to put this in parentheses real good. And then to the nearest tenth, again, you should get about 335.1 centimeters squared. If you're going to put it in the calculator at that step, just be really careful to put parentheses around everything to make sure that your calculator understands what you're trying to type in. And it's really that simple. Knowing the formula for the area of a sector, the formula for the arc length, and knowing how to switch back and forth between degrees and radians.